no se ve. Vaya, pues bueno, ya tenemos lo primero del día, que un tecnólogo no sabe encender un láser, o al menos no se lee. Good morning, everyone. Fabry-Pérot etalons are commonly used in solar astronomy. The reason for the popularity is that they offer fields of view much larger than the ones provided by conventional slit-based spectrographs. And they have also very fast imaging capabilities. This means that they are an excellent choice in order to study the evolution, the dynamics of solar events that take place very fast in just a few seconds and over large fields of view. My name is Francisco Javier Bailén. I work at the Instituto de Astrofísica de Andalucía within the Solar Physics Group, and I'm going to explain you how solar instruments based on etalons work and the main challenges that we face when we design these instruments. Fabry-Pérot etalons, as many of you probably know, are just resonant cavities, optical resonant cavities. They are made of two plane parallel plates with high reflectance in a way that light that enters into the etalon reflects multiple times within the cavity. The transmitted light forms then an interference pattern that is repeated periodically over the spectrum with multiple, actually with infinite resonances. The position of these resonances can be tuned just by changing the separation between the plates, the refractive index, or the incidence angle, as we can see in this figure. Etalons, when combined with a very narrow band filter, allow us to isolate a single order of the resonance, a single resonance of the etalon while suppressing the rest of them. And if we are using also electro-optical, piezoelectrical actuators, we can use that in order to scan a spectral line of interest. If we combine it also with a polarimeter, we can use it in order to get information of the spectrum of the Stokes vector, of the Stokes parameters, that is, to get information on the spectropolarimetric properties of light. And since etalons are used as tunable filters, we can produce these very nice maps of the Stokes parameter over these large fields of view. And we can do this also at each point at which we tune the etalon. If we are observing also a spectral line that is sensitive to the magnetic field, we can infer the magnetic field, the three-dimensional magnetic field, that is the module and direction as we see in this figure, but also we can get information on other physical quantities of interest, such as the plasma velocities of the solar surface temperature. Etalons can be illuminated in two different ways in our instruments. In the collimated configuration, the etalon is placed on a pupil of the instrument, and this pupil is in collimated space. This means that the same area of the etalon is always illuminated across the field of view. And also, since the pupil is placed on collimated space, the illumination received by the etalon will be collimated too. Meanwhile, in the telecentric configuration, the etalon is placed close to a telecentric image plane. This means that each point of the etalon across its aperture is illuminated by an incident cone of rays that has always the same orientation. The main advantage of the collimated configuration is possibly that the whole aperture of the etalon is always illuminated. This means that local defects are averaged out, and also that we should expect the same optical response all across the field of view. In exchange, the transmission profile is shifted across the field of view, and all defects have an impact on the wavefront degradation, on the image quality of the instrument. Let me clarify what I'm referring to when talking about defects. Defects are just irregularities of the etalon plates across its aperture. They can be divided basically in two categories: small-scale defects, which are defects of very high frequency, like the Gaussian defect that we see here, and large-scale defects that usually increase when the etalon aperture also increases, as it happens here for the spherical and for the parallelism defect. Both small-scale and large-scale defects have an impact on the optical quality of the instrument. In fact, the RMS of the wavefront degradation produced by these devices is given by this simple expression, where the first term accounts for an amplification factor that arises simply because of the multiple reflections of light within the cavity. The last factor accounts for the RMS etalon plate's roughness, that is for the deviations of the optical plate's thickness across the aperture of the etalon with respect to the nominal value. We have investigated the impact of these factors on the wavefront degradation of these etalons, and we have found that the amplification factor increases in a nonlinear way as we reduce the spectral resolution of the instrument. This effect is common for both the collimated and the telecentric configuration, and is in fact slightly larger for the telecentric case. As we reduce the F number in the telecentric case, that is, as we make broader the aperture of the incident cone of beams, this effect is even higher. So I want to raise a question now. Do you think, taking a look to this figure, that the collimated configuration is then safer in terms of image quality? Well, the actual answer is no. And the reason for this is that the footprint of the incident beam on the etalon is much, much smaller for the telecentric configuration. This means that the wavefront degradation is only affected by very small scale defects. And this means also that the roughness error, this last term on the equation, is much smaller. It dominates over the larger amplification factor that we have in the telecentric configuration. So usually it is safer to use the telecentric configuration in terms of image quality because it's easier to keep the wavefront degradation under control to achieve diffraction-limited performance. However, the telecentric configuration is not exempt of problems. The most important problem is called pupil apodization. Pupil apodization refers to the fact that the pupil, as seen from the etalon, is not illuminated homogeneously. The reason for this is that at each point of the etalon, we receive a cone of rays, and each ray comes also from a different part of the pupil and with a different incidence angle. This means that at a monochromatic wavelength, the pupil cannot be seen as homogeneously illuminated because the transmission profile of each of these rays is shifted differently. This is a wavelength-dependent effect. It changes across the transmission profile, and this is exactly what we see here, the pupil apodization for different monochromatic wavelengths across the transmission profile. This has an impact on the optical quality of the instrument. In fact, here we see the cross-section of the PSF along the transmission profile of the etalon. And you can see that the core of the PSF is broader in some parts of the spectrum and is narrower in other parts of the spectrum. And where it's narrower, the energy contained by the wings of the PSF is also larger. So there is a transfer of energy between the wings and the core of the PSF, and it changes dramatically across the transmission profile of the etalon. And this is not the only problem with this configuration. There is another important problem. In our instruments, we usually tilt the etalon in order to suppress ghost images on the detector. And we tilt the etalon just a few tenths of a degree. But tilting the etalon, even if we do so a few tenths of a degree, produces an asymmetric illumination of the pupil. Pupil apodization is now asymmetric also. This has consequences on the PSF of the instrument and on the transmission profile. The profiles are now not only asymmetric, but also broader, and they are shifted compared to the collimated configuration. So we have evaluated for the first time the impact of this spectral dependence of the pupil apodization and also the impact of asymmetries on the PSF and on the transmission profile on our measured signals. We have used for that magnetohydrodynamical simulations, like the one that we see there. We see there the intensity at the continuum, the plasma velocities, and the magnetic field over our field of view, which contains a solar pore. And here you can see also the contributions from pupil apodization and from a tilt of the etalon, from this asymmetric pupil apodization. We do not only have these maps of the measured signals, but also we have found that the amplitude of these signals decrease with the inverse of the square of the F number. And this is quite an important result because it's telling us how we must fine-tune the F number of the incident beam in this configuration in order to keep these artificial signals under control. There is another important effect, especially for space instruments, that I want to talk about. In space, we usually employ lithium-novate etalons. Lithium-novate is a wonderful material because we can use it to tune the etalon just by applying an electrical voltage. But it is also an anisotropic uniaxial crystal. And this means that it introduces birefringent effects in our measurements. It modifies the polarization state of light, and that is exactly what we want to measure accurately. So we have analyzed the polarimetric response of these etalons, and we have found that the Muller matrix of these etalons is very symmetric. It's formed by 4 spectral coefficients that are distributed in a symmetrical way. We have 2 of them, B and D, which are of diagonal elements, and then they introduce crosstalk between the different Stokes parameters. And we have found also that the Muller matrix of the etalon can be described as that of a mirror pulsar retarder, both spectrally modulated by the transmission profile of the etalon. We have even assessed the amplitude of these coefficients spectrally across the transmission profile for different incidence angles in the collimated configuration and for different tilts in the telecentric configuration. We have even found that they increase in a nonlinear way as we increase these angles. But what is more important, we have assessed also the polarimetric response in our instruments. And we have found that in the telecentric configuration, I don't know why the images of the plasma velocities are seen this way, like saturated. But anyway, the impact in telecentric configuration is very small. We have found that it is about an order of magnitude smaller than the artificial signals that we found for the pupil apodization effects. And for the collimated configuration is even smaller, and it can disappear even if the etalon is placed after the analyzer. So to sum up, I just want to remark 3 highlights. We have provided first a general novel overview of the limitations of these instruments from an imaging, polarimetric, and spectral point of view. We have provided also new knowledge on the limitations of these instruments. What is probably the most important thing, we have provided also a new set of tools in order to fine-tune the optical requirements of our instruments, in order to design instruments that will be more sensitive and more accurate in the future. That's all. Thank you very much.